Hey everyone, we're excited to show what Skynet was able to achieve in our localized mesh communication network this semester. My name is Alex Krebs.
I'm Cameron Anderson.
I'm Connor Patton.
And I'm John Evans.
So as a general overview, we worked on creating a mesh network using LoRa or long-range antennas. This involved using a phone application, a drone, and a client device. In the phone application, we wanted to make sure we could send text to others in the network, view locations of network participants on maps, and use two different map views depending on internet connectivity. We also want to make sure the drone could be used to increase the range of messages or message transitions so that participants could be farther away from each other. On the client device, we ended up using an STM32 Blue Pill microcontroller, a custom designed PCB, and a 3D printed device enclosure. For some of the details of the phone application, we wanted to make sure that we could distinguish GPS data, messages, and drone commands, and did this by using various phone message protocols to separate them out accordingly. We made sure that messages were forwarded throughout the mesh network so all participants could receive them, and only those dedicated to receive the message would actually display them. We also tried to confirm that messages were received in the mesh network, and if there was any trouble confirming this, we would status it to the user. We also provide maps for clients so they could see where their movements were relative to others and could even be able to find others in the mesh network. The user interface of the phone application allowed for people to connect to the Bluetooth device that will be on the client device. Once it was connected, it would display that and people could start sending messages. They could send messages to either all participants of the mesh network or individual participants of the mesh network, as shown in the third image here. This allows us to send to specifically John in this instance, the message, "Hey John," in the fourth image. John is then able to respond with, "Hey, what's up?" And we see that it came from him, where his name is given before a colon and then the message that he sent. When someone tries to view the map in this application, they have two options depending on internet connectivity. If there is no internet connectivity found at that time, it will display the image on the right, where there's a very simple map that shows relative positions and even the central location. This is used so that we can find out where people are and be able to connect with people easier. If there is an internet connectivity, it will use the Google Maps API, and John will explain that.
Thanks, Alex. Like was said, for the online map, I wanted to integrate the Google Maps API so that we would be able to not only see where other individuals were inside of the network, but also be able to real-time see where you are in relation to other things on the map, as well as use some of the built-in Google Maps functionality, such as getting directions to other places. On top of just being able to see where other participants are on the map, at the bottom of the screen, you're able to see 4 different buttons. These buttons are the way that the phone app integrates with the drone in the network. They allow us to first center the drone in the middle of all the participants. This allows us to extend the range of the network and have it in an optimal place to make sure that all participants have a good connection. We're able to make the drone take off. We are able to make the drone return to home or return to the starting location, as well as make the drone stop where it is and make a safe landing, which leads us into more details, which will be shared by Connor about the drone.
So as mentioned earlier, the drone's really used to increase the range of the entire network. This is very beneficial in environments such as mountains, where you might have a range in between each node. In those cases, being able to fly the drone up in between each user allows users to maintain line of sight between everyone. All right, so here is the Navio 2 board that we used. It's a Raspberry Pi hat. The hat sits on top of the Raspberry Pi, and it includes all the sensors necessary for flight. This includes a GNSS receiver for GPS, as well as an IMU and a barometer. All these sensors come together to allow for very clean and efficient flight. Now, in order to allow the Pi to communicate with the flight controller, we use the DroneKit API. This framework facilitates making autonomous applications, all of which are designed around sending Mavlink messages. Separately, a LoRa radio can be used, in this case, connected over a UART port and communicate and use with serial communication, where the received messages on the network are forwarded, and other drone commands are handled as such. Here's a little overview of the communication flow. Messages come through on the LoRa radio from each of the different nodes. Here on the Pi, they get interpreted as just standard messages or drone commands. The standard messages just get simply forwarded back through the mesh network to improve the range. If it is a drone command, it is then sent to a program which uses the DroneKit API to convert the command into a Mavlink command, which the Navio flight controller is able to understand. Once it has that command, it's able to execute that and go to a certain location or take off or return to home. So here's a close-up of the Navio board on top of the Pi on our drone. You can see the GPS module as well as some of the sensors on board. Most of the build process went smoothly, but as you can see on the right, there were a few mishaps, including a broken prop, as well as several sliced cables, all of which made the process a little bit slower. But
now we're going to go a little bit more into the client devices themselves that we designed. They are using a UART serial communication with the LoRa radios as well as the Bluetooth radios. These devices act as a simple interface in between the phone and the long-range network that we have set up. We designed custom PCBs for them to ensure that the assembly doesn't cause any issues in the system, as well as the encasings to make sure that nothing gets jumbled around or damaged. For the microcontroller, the left image that you can see here was an early prototype of our system that I had put together. It was using a larger board just to give a proof of concept that we could use a Bluetooth radio to connect to a phone and then send a message using the long-range radio. Ultimately, we decided to go with the STM32F1 family of microcontrollers. This specific board that we used is known as the STM32 Blue Pill. And we decided to go with it as it met all of the requirements that we needed for the UART serial communication, as well as a nice compact form factor. On the right of the slide here, you can see an example of another set of devices that we had during development in order to prove that we were getting serial communication through Bluetooth radios correctly forwarded through the microcontrollers.
And after all of our proof of concept was done and most of our troubleshooting was complete, we were able to design and fabricate a custom PCB for this project. So on the left here is the schematic and layout that shows all of the different components and how they're connected, making sure that every necessary connection is made. And then on the right is the PCB design filled out and shown in a 3D model with some of our custom logos and some text. And with this PCB, we were able to make a slick and compact client device. So here I pointed out the different components, and we were able to make it so compact because we stacked components on both sides of the PCB. So the LoRa antenna was attached at one end, and then on the top was the Blue Pill microcontroller, and on the underside was the Bluetooth module, as well as some components for the power circuit. In order to have a freestanding portable client device, we needed to include this power circuit so that it could run off of a lithium-ion battery. So with a 1100 milliamp hour battery and a switch and a micro USB charging port, we were able to create a charge discharge circuit. The LEDs you see up at the top are status LEDs for the power circuit, with one being when the client device is powered on and the other one for when it is charging. Once the PCBs and components were all put together, we designed and printed a case, and the case was just simple enough and has the holes necessary to have the LEDs, the switch, and the LoRa module, as well as the charging port come out. So the left-hand side, you can see the print in the CAD software, and on the right are the printed out final versions of our case. Due to the semester being mostly online because of COVID-19, a lot of the progress of this project was done individually. And at the end, when things were working, we had to come together and integrate everything. So this video shows the very first time that we were able to send a drone command across the network from the phone app. And then after some more verification and making sure that we were safe to go outside, we attached the props and did some test flights outside. So this first video is the first time that we were able to get it off the ground, as you can see, a little bit to our own surprise. And then another video shows, after some changes to the autopilot, a clean takeoff with a command from the phone. So with all of that, we were able to create the localized mesh network that we sought to create. We were able to get a fully integrated system where we could have multiple clients, including multiple phones and a drone. We were able to send messages across the network to the drone, and if the message was not intended for the drone would forward the message to other nodes in the network. And then users were able to send the specific drone commands via the drone or via the phone application. In the end, we are very happy, very proud with the project we were able to complete. And from the Skynet team, we thank you for watching our presentation.